These are electricity conceptual questions, number 1 through number 10. And the first one says, in order for there to be a flow of charge from one place to the other, you need to have two things. And those two things that you need, one of them is you have to have a wire or a conductor. So you'll see that conductor right there. And then you have to have a push. And remember, the battery provides the push for the current to flow through the circuit. So that is number 1. For number 2, so let's get this to number 2. For number 2, we've got in solid conductors, electric current is the flow of electrons. You'll see that the electron is right here, and it's actually kind of moving very randomly, but it drifts towards the right. The current, on the other hand, is the flow of positive charge, and it actually moves in the opposite direction. So electric current is the flow of electrons, but the charge actually flows in the opposite direction, which is very strange for some people, but you should just work right through it. Electrons move in an electric circuit by interacting with just an established electric field. So here we've got that very thing. And these are electricity conceptual questions, number 1 through number 10. For the first one, it says, in order for there to be a flow of charge from one place to another, there must be, and there are actually two things that you need here. One of those things is a wire. So you'll notice you'll see the wire going to and from the light bulb, and also going from and to the battery. And then you also need a potential difference, and so that potential difference is provided by the battery itself. Remember the positive and the negative side, that provides the potential, and once the battery runs out, then you don't have that potential difference anymore. The number 2 says in solid conductors, so we're looking at maybe a wire made out of copper. Electric current is the flow of electrons. You'll notice that there is an electron, and that electron, let me click this really quick here. That electron is right here. It's actually moving in this kind of random path. And you'll notice that it just moves and drifts from left to right very slowly. When it does that, it actually creates current flowing in the opposite direction. So we say that current is what it does, it actually moves in that opposite directions. So electric current is the flow of electrons that creates the current that then flows in the opposite direction. For number 3, electrons move in an electric circuit. There is an electron in this one, and you'll see the electron right here, and it interacts with an established electron field. There has to be an electric field, so you'll see these, all of these arrows, and they're all pointing towards the negative charge on the inside, so that electron moves against that electric field. For number 4, number 4 says the unit of current is an amp, and sometimes they'll call it an ampere, but most of the time we hear the word amp. An example in number 5 of a voltage source, something that can carry voltage, could be any of the things that you see here. A dry cell, similar to a lamp or a lantern battery would be a dry cell. A generator, that's something that you would put gasoline into, and then when you start it, it will generate electricity. A battery, we've all seen batteries. And if you remember, we rubbed a rubber rod with some fur, and that also created some voltage. And so all of those will carry voltage. For number 6, resistance depends on a wire's thickness. It depends on its conductivity, and it depends on its length. So it actually depends on each and every one of these. If you think about a car going through a tunnel, it'd be the same thing. How wide that tunnel is, or how big around the tunnel is, will allow you to have more cars go through. The more conductivity, the less resistance, and then the shorter the wire, the less resistance. So we actually want a pretty short tunnel, but we also want that tunnel to be really wide, and that way we can get more cars through it. For number 7, we have, compared to thin wires, electrical resistance is in thick wires is much less. So remember, we did say in that last one, it's easier to go through a large tunnel because there's less resistance. You could also think about if I have a garden hose and it's not very big, and then I have a great big drain pipe and it's 10 times the size, we can get a lot more water through that drain pipe than I can through that garden hose in the same amount of time. For number 8, For most conductors, as their temperature increases, their resistance also increases. So essentially, when a wire gets hot, it's much harder to travel through the wire. So if you got up and moved around the classroom, it would be really hard to move from one place to the other if everybody was banging into each other. If everybody's seated and they're very calm, like in a cold wire, it's very easy to go from one place to the other. But if you have a hot wire, then you end up with a lot of people moving around a lot, and it's very difficult to get by those people. So if you're standing here and they're bumping into you, it's a lot harder to do. For number 9, resistance is measured in ohms, and that symbol is this upside down looking U. We call this omega. So this is omega. It's a Greek letter. And when we measure it, that's essentially what's measured in. So when you do your problems, you want to make sure you use that symbol. You can also just write the word ohms. And finally, number 10, a woman experiences an electric shock. The electrons making the shock actually come from the woman's body. They don't come from the wire itself. They just actually come from the woman's body. And that's the end of number 1 through 10, including the dog barking.